Good afternoon, everybody. Can you hear me okay? Yes, you can. Fantastic. Well, a very big and warm welcome to you all for this very special afternoon of space science and space exploration. Welcome also to the people who are watching via the live webcast. My name is Lucie Green and I'm a space scientist here at UCL, so I'm delighted to be the chair of this afternoon where we have two very special guests from NASA. So I'm going to introduce them both and then they will be giving their presentations, and then I'm hoping we'll have about 15 to 20 minutes for questions afterwards, and then we'll wrap up by 3:30 is the plan. So, on a very special day for space science in general, I should say as well, because of course we've got the European Space Agency Philae probe landing on a comet, hopefully, fingers crossed, this afternoon. So after the talk, please do go and have a look and see how that mission's getting on. So we're going to be hearing from our first speaker, which is Dr. Ellen Stofan, who is Chief Scientist at NASA. So she advises right to the very top about the science program. Now, Ellen has a background in geology, but that enabled her to go on and then do planetary science, and she's worked on studying planets such as Mars and Venus, but she's also led a mission proposal to go to the largest moon of Saturn, which is called Titan, and she had an idea to send a floating probe to land on one of the seas of this moon, Titan. Absolutely fascinating. There's a quote from Ellen, which I read earlier on. And she said that NASA is the keeper of the future. So I'm delighted to be able to say that this afternoon she'll be talking about that. Following Ellen will be Professor David Miller, who's the Chief Technologist at NASA. Now, Dave has the rather interesting job of working between NASA, industry, and academia to look at the future technology and innovation in space science. So, fascinating role that I can't wait to hear more about. But I should also say that he is the Jerome C. Hunsaker Professor of Aeronautics and Astronautics at MIT. So that's David Miller. But first of all, let me please welcome to the stage Ellen Stofan.
Thank you. Is that on? Yeah, it's on. It's really a pleasure to be here today. For those of you who don't know, I'm actually a long-term associate of UCL. I first came in, this is going to be a really long time ago. I think it was about 1994. And at various times I've been an honorary researcher and an honorary professor here at UCL. So it's really a pleasure to be back here today. It's always really fun for me to be able to come and talk to audiences about our plans for the future. And one thing I'm going to come back again and again to, when I talk about NASA's exploration program and the journey to Mars, this isn't really just NASA on its own. Because obviously an undertaking like trying to send humans to Mars is a really big undertaking, and NASA can't do it alone. And so right now we're actually working with 16 space agencies around the globe, including the UK Space Agency, ESA, Russia, among others, to plan what's called the Global Exploration Roadmap, which you can actually find on the web, that lays out what the international vision is for the exploration of Mars. And the fact that if we're going to do this, unlike the lunar program, which was dominantly the US sending humans to the moon, when we send humans to Mars, it's going to be done internationally. Now, as chief scientist at NASA, and I always think I have the best title besides astronaut. Astronaut is a way better title, we can all agree. I get to look over all of the science that we do at NASA, and the extent of it is quite amazing. When you think of the studies that we do of our own sun, obviously extremely dynamic, solar flares, coronal mass ejections that send particles streaming towards the Earth, something that we need to understand in terms of being able to protect our satellites in orbit, our astronauts in orbit, but something that we worry about even more for sending humans to Mars, where for 8 months at least on the way to Mars, they'll be outside the Earth's protective magnetic field, exposed to not just solar radiation, but also cosmic radiation. So understanding the behavior of the sun, and again, it's fascinating to me since this isn't my field, is how much we have to learn about the sun at this point. You know, we have no ability right now to predict coronal mass ejections to predict solar flares. We are starting to begin to get signs of areas where they're more likely to occur, but in terms of a real understanding, which then allows you to go to a predictive mode, we're still pretty far. So a lot of work left to be done for the sun. We have a network of satellites that are mostly in observing mode to give a kind of an early warning system, but also to monitor and make all kinds of measurements at the sun. Obviously, most people are quite familiar with the work that we do studying the universe with assets like the Hubble Space Telescope, which amazingly enough is celebrating its 25th anniversary. Such an amazing tool that has been able to look very deep into the universe, been able to study the planets. Just recently, we used it to study comet sighting springs that was going by Mars. So an amazing astrophysical telescope that we're using for multiple purposes. Of course, we're excited in astrophysics that our next big observatory, the James Webb Space Telescope, will launch in 2018. James Webb will be able to see even deeper into the universe, so even further in time, back to the earliest moments after the Big Bang. It will also be able to study the atmospheres of extrasolar planets, something we're really looking forward to. An area that I've really been learning a lot on this job is the International Space Station and the research that we do in microgravity. Microgravity is a really unique environment. For example, there's phases of combustion that we've discovered. We're doing research in microgravity. You can do all kinds of interesting experiments with materials. An amazing site, but I'll talk a little bit later about the human research that we've been doing. Because since we evolved in a 1G environment, you take us out of that environment and we basically don't work very well. From our cardiovascular system to just about every aspect of the human body doesn't function very well in microgravity. Again, you could say, oh, we'll stay out of microgravity then. But you know, as humans, that's not what we want to do. We want to go to Mars. Again, 8 months there, 8 months back. How do you make it so that humans can function on the surface of Mars when we land, not weeks later? So that's a lot of the research we're doing on the International Space Station. In terms of the solar system, we have the Juno probe on its way to Jupiter. We have New Horizons, which will reach Pluto in July of next year, which we're really excited about. And Hubble, again, showing Hubble's usefulness, just found hopefully a few follow-on targets for New Horizons, so that after it goes by Pluto, we'll be able to actually go and image another Kuiper Belt object after Pluto. All the way to the inner solar system, where we have the Messenger spacecraft at Mercury, and then obviously our large number of spacecraft at Mars that I'll be talking about. And then, of course, the Earth. And I'm going to come back to the Earth before David talks. But we have 17 satellites in orbit around the Earth, basically measuring every aspect that you could think of the Earth's dynamic systems, from the state of the land to the state of the oceans, the atmosphere, and how they're changing. This is the Hubble deep field image, where they just pointed Hubble at the darkest part of the sky and tried to take the deepest, furthest image they could find. And obviously what was so fascinating about this image is not only I think it's one of the prettiest images that's come back from Hubble, was first of all how many galaxies, of course, were in an area they thought was empty-ish. It wasn't at all empty, but also the fact that galaxies had clearly formed very early. There's a lot of debate about when galaxies actually would form. So, fascinating image. But I also like this image because it gets back to something that we've been discovering recently, is what is up there in that night sky. When you go out and you look at the night sky, you see a dark area. Well, it's not dark. It's full of galaxies, and those galaxies are full of planets. Every star that you are looking at in the night sky, when you look up, if you can see from the lights of London. Okay, go out of London, then look up at the night sky. Every star you're looking at, you are probably looking at a planetary system around that star. Now, how do we know that? We basically are pretty sure of that because of what we've been finding from the Kepler Space Telescope. Kepler looked at a small area of the sky, found over 2,500 planet candidates. the mission was only operational for about 2 or 3 years. We're now following on. It lost part of its, basically its pointing system, but we're following it on with a mission we call K2 or Kepler 2 that will just look at a different part of the sky and hopefully continue finding some planet candidates. Again, over 2,500 planet candidates, and because Kepler had the ability to detect much smaller transiting planets, we found a huge number in what we call the super Earth size, so somewhere bigger than the Earth, smaller than Neptune. Now, who cares? Okay, we're getting back to this point of saying, where can we find an Earth-like planet? How many habitable worlds are there around other stars? Okay, has anybody seen Interstellar? Sorry, I just saw Interstellar a few days ago, and I go to talk about this, and all of a sudden I'm like back in this weird movie, so anyway, sorry. You know, how many habitable planets are there out there? What are the characteristics of a habitable planet? And again, the fun thing is with JWST, we're going to be able to take some of these planet candidates that we identified with Kepler and start looking at their atmospheres. So how are we going to recognize a habitable planet when we see one? When what we can do at this point is study its atmospheric composition. Okay, you're going to look for water, right? You're going to look for maybe something changing. Can we stare at it long enough that we can see any fluctuations in the atmosphere that would say there are dynamic processes taking place? What's the gas mixture you're going to look for? So we were able to start taking, to some extent, what used to be science fiction and say, okay, now we've got to start making some concrete predictions because we're going to have the ability to start looking at these atmospheres with JWST. In between now and JWST, we're going to have another satellite called TESS, or the Transiting Exoplanet Survey Satellite, that is going to find, basically, the prediction is with TESS, we'll be able to identify an Earth-sized planet a week. And so again, the world is changing because what it's doing is it's taking our views of what solar systems are like, what planets are like, and it's going to completely change it because we're getting so much data. We've already had to, based on the planets we've identified to date, because Kepler was not only able to see planets, we've actually identified many multi-planet systems, 5-planet systems, 7-planet systems, a lot of 3-planet systems. We've already had to take our basic model of how solar systems form and had to massively change it because it turns out most planetary systems don't really look like ours, where you have rocky planets close to a sun and gas giants further out. Things are all mixed up, planets are in weird orbits, and so we're having to revise our models to understand the new data. Now, when we think about habitable planets, one of the fundamental questions that we're trying to answer, which actually shows up in all of NASA's governing documents, is a really simple question. Are we alone? Is there life in our solar system? Is there life beyond our solar system? Based on what we know about life here on Earth, it evolved fairly rapidly after the Earth formed, right? Earth formed 4.5 billion years ago. By about 3.8, 3.9, there's evidence of very simple forms of life on Earth. To get to us took a really long time, billions of years. Billions of years of a stable-ish environment where evolution could proceed and you could go from simple life forms to complex life forms. So, okay, when we go out into the solar system, we say, first of all, we know the building blocks of life, organic compounds, have been delivered all over the solar system by comets and asteroids. We know lots of places in the solar system have some sort of source of energy, lightning, volcanoes. What we really look for, based on what we know about the Earth, is liquid water, because we think liquid water is really important for the formation of life. It actually has, I was learning this recently, it actually has something to do with the dipolarity of the water molecule that they think actually helps these reactions proceed and you to get move towards the formation of RNA and DNA and getting life. So if we think that liquid water is a necessity, then where are we going to go? And obviously the center planet is the planet that we've been the most focused on, Mars. We know, and the Curiosity rover, which is right now climbing that mountain, Mount Sharp, Curiosity has told us that not only did Mars have water on the surface, which we've known for a really long time, but that water persisted for very long periods of time, tens, hundreds of millions of years. Okay, that's critical to go back to that point I talked about earlier about stability of environment. So can we find somewhere on Mars with our rovers, like the Curiosity rover, where we can demonstrate, did life exist? Okay, how are you going to design that experiment? What are you going to look for? Organic compounds, okay, but those can actually form by inorganic processes. They don't have to be, it doesn't have something living to get an organic compound. So that's certainly something we're looking for, chemical signs of life. Can we find something that looks like an amino acid? Those are the kind of things we're looking for. Obviously, you'd love to find a fossil, right? Okay, not that lucky, much more difficult. If something's alive, how are you going to prove it's alive? We've already seen from the Mars meteorite that some of you might have heard of, one that came from Antarctica called ALH 84001. It was a Martian meteorite that was found about 15 years ago. And a group analyzed it and said, we think we see things in here that look like they could be fossils. Huge amount of debate in the scientific community. And the scientific community basically came forward and said, no, we think those are all produced by inorganic processes. We don't think it's evidence of life. And so as you think about our exploration of Mars that we're doing in the future with Curiosity, our future Mars 2020 mission, which is going to be a rover pretty much like Curiosity, outfitted with a little different instruments, the ExoMars rover, how are we going to definitively say we've found life on Mars? I think it's a huge question because unlike some people who say that the scientists like to agree, scientists actually love to argue, not a surprise to many people here. And I actually have a strong bias that it's actually going to take humans on the surface of Mars, astrobiologists and geologists picking up rocks, cracking them open, having a lab on Mars where you can actually have lots of samples and lots of debate, lots of tests, to really be able to convince the scientific community that we've detected unambiguously that life did evolve on Mars. Before I go on with more on Mars, where else would we go in the solar system? Europa, up in the upper right, is thick icy crust, moon of Jupiter, thick icy crust, ocean underneath the icy crust, which causes the icy crust to move around, forming all those big cracks on the surface. At the center of Europa is a rocky core that's being pulled on by Jupiter all the time. Some of you might know of Jupiter's moon Io, that's got volcanoes all over the surface, kind of looks like a pizza. Jupiter's pulling on the inside of Europa just like it's pulling on the inside of Io, making all those volcanoes erupt. So we think you have an icy crust, an ocean, and at the base of that ocean, probably volcanic activity. That makes people who do astrobiology think about black smokers on the surface of Earth's oceans. These volcanic vents that actually tend to be very rich in life. So a lot of people think that Europa is actually the most likely place in the solar system that we would detect life. Okay, but bummer. What we have is a hugely ionizing radiation coming from Jupiter and a thick icy crust with some orange gunk on it that we don't know what the composition of it is. So how are we going to figure out? I just went on about how hard it might be to find life on Mars where we can actually analyze the rocks. Now we have Europa, where the problem's even more difficult. The good thing is, and this is Saturn's moon, Enceladus, same issue, thick icy crust, water underneath it. Enceladus has geysers. That liquid ocean is basically erupting out of the interior of Enceladus. We actually flew the Cassini spacecraft through those plumes and measured that there's water. They are water plumes coming out. And there's all kinds of really complex organic compounds, but our mass spectrometer wasn't good enough to tell us what they are. Back in December, the Hubble Space Telescope observed water plumes coming out of the south pole of Europa. We're actually in the process right now of designing the next mission to Europa. There's a call that went out for instruments. They'll be selected sometime this winter. But what we're hoping is that we can first of all demonstrate that the plumes are really there. There's only been one observation of them. But then fly a spacecraft through Europa's plumes. And it's a lot more convenient if that ocean is spitting out at you rather than having to melt down through the crust of Europa, which would be hugely technologically challenging. So we're pretty excited about Europa. A harder case to make, but one I like to make, is that Titan, which is the moon up there, is one of the most interesting places to go in the solar system if you're thinking about life. Now, Titan doesn't have water on its surface, but it does have a liquid. It has liquid ethane and methane seas, and that's actually sunlight reflecting off a sea at the North Pole. Okay, so maybe you don't need water. Maybe we're wrong based on what we know about life on Earth. Titan would be the place to go to test that theory. Okay, that's the wrong computer. There we go. Okay, so back to Mars. We've landed on Mars actually 8 times successfully. These are 5 of the different places. And again, what have we been doing all that time with all those Mars landers? Well, we've been trying to follow the water, make the case. Where's the water? What are its characteristics? Is it acidic? Was it more benign, so potentially life could evolve? What are the exact characteristics of Mars that make us think it was potentially a habitable planet? And what are the most likely environments that you could go to actually determine that? And as a geologist, we also like to study all these rocks. What are their composition? What does that tell us about the history of Mars, which gives us clues then to the history of the evolution of its atmosphere. And again, a lot of this is preparatory to actually sending humans to Mars, which we would like to do in the 2030s. And this is how we're going to get there, and David's going to talk more about this. Right now, we consider ourselves to be in an Earth-reliant phase. We're using the International Space Station to understand more about, again, these effects of microgravity on the human body. Then we'd like to move out to the proving ground, which is the area around the moon where you could go out to a Lagrange point or in cislunar space where you could say, let's test things like life support systems. Let's test different technologies in a place where you could make it back to the Earth safely. In the meantime, we're using all our assets at Mars to try to characterize the Mars environment, not just from that scientific point of view that I've been talking about, but from a point of view of being able to send humans there safely. This is the MAVEN spacecraft, an artist's conception, that went into orbit around Mars in October of this year. MAVEN is studying the atmosphere and atmospheric loss processes at Mars, and this is just some of the first data that's coming back showing carbon, oxygen, and hydrogen around Mars. Now, we're particularly interested, obviously, from a scientific point of view, what happened to the water on Mars, on the water that went up to the top of the atmosphere and got stripped away from Mars. We think that's what happened to a lot of the water on the planet. But MAVEN's also really important because it's giving us a lot of information about the structure and density of the atmosphere and how it varies over time. Now, that's important because we want to land a lot of mass onto the surface of Mars. And right now, we only know how to safely land something about the size of Curiosity. Okay, that's not nearly big enough compared to sending, say, a crew of 3 humans down to the surface, not to mention the equipment they'd need, in situ resource utilization, all kinds of equipment that you would need to get down to the surface of Mars. So studying the Martian atmosphere, understanding how it varies is really important for getting ready to send humans there. The other things we're doing, for example, with the Curiosity rover, is looking at radiation effects. I'd already talked about the fact that we worry about the dose of radiation that humans will get on the way to Mars, especially cosmic radiation, which is very hard to shield against. But on Mars Curiosity, we actually have a radiation detection experiment that measured the radiation environment on the way to Mars, and it was about as bad, or not quite as we thought it would be, but it's also been measuring it on the surface of Mars, which has been a little less bad than we thought it would be. So extremely important to quantify it to better understand how to protect astronauts. Dust effects is another important. We need to understand the properties of the Martian dust. It turned out with the Apollo missions, when they would go out and work on the surface of the moon, they'd come back in the spacecraft, the lunar module, and they had dust on their spacesuits. Okay, now they deorbit, go into zero gravity, all that dust started floating around, started inhaling it, got into the equipment. Not a good thing. Dust is bad for astronauts. So we need to understand the properties of the dust on Mars in order to make it safe for the astronauts to not breathe it and to have it not get into our equipment. And crew health. Not just things like the radiation, not just things like dust, but eating. How are we going to feed people for that length of time? How are we going to make sure that mentally mental health-wise, that this journey is not too taxing. So a whole range of issues with human health that we're working on the space station, including the fact of the pressure in your head goes up. It's a visual syndrome where since the pressure in your head goes up, it puts pressure on the optic nerve, and some of the astronauts suffer permanent vision damage from that. How can you mitigate that effect? Bone density loss. Exercise helps, not completely. How can we mitigate that? So a whole series of things that we're working on the International Space Station. And we actually, in very NASA form, we have a whole flow chart with little diagrams in red, green, and yellow of how are we going to buy down these risks, especially over the next 10 years where we have the International Space Station, to do experiments, to develop the technologies we need, and in order to ensure that when astronauts get to Mars, they'll be ready to work. The International Space Station is also being increasingly used as a platform for Earth science. This is brand new data from an instrument called RapidScat, which is measuring surface ocean winds that just went up on the, onto the space station a few months ago. So we are also able to use it uniquely as an Earth science program. The QuickScat, which is our normal way that we measure surface ocean winds, is in more of a polar orbit, and it's designed to measure, make measurements at the same time of the day. The space station crosses, especially the tropics, where we're really interested in winds because of large-scale storms, crosses at different times of the day. So you're able to use those two data sets in a very complementary way. So it turns out that the ISS is actually a great platform for Earth science. Now, obviously, Earth science is of critical importance at all times, but especially right now. This video is cycling through deviations from average surface temperature. And again, these are data, this is not a model, starting in the 1800s and going up to the present time. And you guys all know the punchline. The Earth is getting warmer. And again, this is data, not a model, though we do have these data combined with models that run out, that I've seen, that run out to 2050, 2100. And you can well understand that what happens is the Earth just gets redder and redder and redder. But pay special attention here to the Antarctic Peninsula, the West Antarctic, and the Arctic. You'll notice that the effects of the warming are actually not uniform. The Arctic has gotten much warmer than the rest of the planet, and interestingly, so has West Antarctica. This is for 2014, the Arctic sea ice minimum level that was taken. So this is the maximum extent and then the minimum extent. And obviously a huge concern of this is the sea ice is actually also, by the way, it's not just less extent, it's also much thinner. And obviously part of our concern for this is in the Arctic region, when you take away the ice in the summer, you expose a lot more dark seawater, absorbs a lot more sunlight. That energy goes back into the climate system. And there's a huge amount of debate right now in that community about whether that's actually affecting our weather on a short-term basis. In DC last year, Washington, DC, you guys had a mild winter. We had a horribly cold, unusual winter. The polar vortex came down and made it very cold, and everybody whined about it. But there's a big concern. Okay, things are rapidly changing in the Arctic. All right, if you're in the Arctic, climate change is not a model. It's something that's happening every day. And so understanding what those climate effects are on our weather is something that we're still trying to figure out. And unfortunately, it's not a case of needing more data. It's needing more years to understand exactly what's going on. All right, in addition to studying the Arctic, we're also down in the Antarctic. This is the maximum sea ice extent for this year, this past year. In the Antarctic ice actually had a further extent this year because of currents and winds, but also thinner in places. And right now, the US had the European Space Agency has a satellite called Cryosat that UCL has had a long involvement with. In the US, we had a satellite called ICESat that stopped, I think, in 2008, 2005. And we're not going to have ICESat 2 until 2016, 2017. So in between having coverage of the polar regions, where we've been using an airplane mounted with measurements. In the summer, we take it up to the Arctic. In the winter, we take it down to the Antarctic. That's Northern Hemisphere season reference. And I actually just went down 2 weeks ago and flew. These are actually my photos. We flew over an ice stream in Antarctica, just to the east of the Antarctic Peninsula, where the glaciers are accelerating greatly. West Antarctica is a particular area of concern because the ice shelves have been collapsing, allowing the glaciers to move much more rapidly. We know we've got seawater encroaching under the glaciers, up to potentially a half meter of sea level rise alone by 2100, just from the West Antarctic region. And that number is actually not included in the IPCC reports, because at the time those were put together, their sea level rise estimates, it was regarded as being a little controversial, whereas the measurements that we've been making through our international satellites say that West Antarctica, where that warming has been more concentrated, is a lot more unstable than we would like. Now, if you go to the other spectrum of saying, okay, here's area where we're taking land ice, putting it into the ocean, we actually have also huge issues with drought. This is GRACE data, which is gravity data over California. And what you're seeing here is, since 2002, basically, California's been in a huge drought. And what's been happening is they've actually been sucking all the water out of the aquifer. And so what you're seeing there is the ground going down as we've taken water out of the aquifer. We also see the same thing occurring in areas of India where there's a drought. So really worrying signs right now of climate change. So what is NASA's role? Our role is to make measurements, to try to say, this is what's happening here. Can we improve the measurements to make models better? Just this year alone, I mentioned RapidScat. We launched a mission called GPM, the Global Precipitation Measurement Corps, measuring precipitation around the globe every 3 hours. The Orbiting Carbon Observatory, which is measuring sources and sinks of carbon, obviously really important to trying to understand what's going on with the climate. Cloud aerosols we're going to send up to the space station in about a month. Aerosols basically are really important for cloud formation, and their role in climate change is really critical. And then we have a mission called SMAP, the Soil Moisture Active Passive, that's taking that other part of the water cycle, saying, where is soil moisture, how is it varying? Again, important for understanding weather and climate, but also on a practical level for understanding potential agricultural yields, helping farmers. So a really critical set of data. Oops, God, I keep doing that. Now, all these things I've been talking about, the exciting thing is there's actually a way in some of these areas for people to participate. And I urge you to go to a site called nasa.gov. It's called NASA Solve, where we have opportunities for things like app challenges, technology challenges, but there's also citizen science on there. We have a program that can help you. You can look at dust disks around stars and help identify candidates for future observations in terms for looking for extrasolar planets. There's Mars citizen science activities where you're actually doing science on these sites that people are actually using in their research. So really cool stuff at that website. I urge you to go take a look at it. Now, for everything I've been talking about has been the science side of exploration. Why do we want to go to Mars? What are we going to do once we get there? But for NASA, we're actually split up into different divisions: human exploration, science, and technology. So it's actually a challenge for us internally of how do we all work together on a big endeavor like sending humans to Mars? So I've been talking about the science part, and now the Chief Technologist, David Miller, is going to talk about the science part, and then we'll take questions at the end.
So I have the third best title at NASA, and that's because technology always has to be developed with a customer in mind, and science and exploration is the customer for technology at NASA. So Ellen's my boss, so that's why I got the third best title. So first, let me tell you what I do at NASA. When I first got offered the position about 8 months ago, my wife asked me, so what does a chief technologist do? And I said, I have no clue. So I've been trying to figure that out. So here's the best I've sort of put together. Starting in the upper left, sort of the 10 o'clock position, I help with strategizing and prioritizing technology investments at NASA. The bottom left, after we make those investments, I track the progress, or my team helps track the progress, so we can decide what's bearing fruit, what should we stop, and how should we re-steer those investments. At the 6 o'clock position, I engage with the external community, academia, such as yourself at events like this, and industry and other government agencies and so forth. Over here on the bottom right, we also participate in ways to spur innovation through challenges and competitions and prizes and things like that. And in the upper right, my office leads the tech transfer through industry and so forth. And probably the most important part is both Ellen and I get to advise the administrator, the boss at NASA, about, I advise on technology and you advise on science, and then they make decisions. So when I came to NASA with my professor hat on, I was looking at the different areas that we work on in terms of technology, and there's 15 of them. So my first urge was to do pattern recognition. I wanted to see, are they working on the things I'm interested in? Since they hired me, I assumed they were, but I wanted to check. So probably to give you the best idea of where I come from in the technology world, is I do modeling and simulation in support of robotic and autonomous systems, as well as, I didn't look for this one, large space structures right here, and mostly focused on science instruments. So I've worked a lot with the astrophysics community, but I'm very interested in all the other areas as well. So luckily I found that there were some areas for me to provide some expertise. So technology as a mission directorate at NASA is kind of a new thing. It did exist, then it didn't for various reasons, and then it's reemerged over the last 4 years. And one of the reasons is it's sometimes hard to think about the importance of technology in making these missions happen. You know, building rockets to send humans through the solar system is a very obvious and sort of in-your-face kind of activity that people can, really get their hands around. So is the science. But this technology is something that occurs in the background, and sometimes it's a little out of sight and out of mind. So part of my job is to get it in sight and in the mind of the various stakeholders. So the way I like to think about technology is you think about a toolbox that you're going to use to take to a construction site and build things as an engineer, let's say. Well, the technology is really the set of tools that you put in that toolbox. So the better the tools, the better the missions that the engineers can build. And the better the missions, the more exotic and interesting science that Ellen's team can achieve. So we're sort of in the background, but I think we're essential to doing these ever more aggressive missions that the explorers and the scientists come up with. It's also important to remember it's not just about performance. It's not just being able to get bigger rockets or better detectors. It's also about, under constrained budgets, to get a more affordable and more reliable missions. And technology plays an important role in that area as well. And finally, it provides a way to tap into the community that extends beyond NASA. And that is researchers in the university setting and industry and so forth, especially at fundamental technology development, really engaging with the universities, getting them involved and excited about NASA's mission and having NASA benefit from the insights that they bring to the table. So let me give you an overview of sort of where NASA does its business and where technology plays there, because my role is to look across all of NASA, not just in our one directorate that has to do with space technology. So let me tell you about the directorates. There are 4 of them. The first one up here is Human Exploration and Operations. That's the directorate where we operate the International Space Station, and we're also developing exploration systems for humans beyond low Earth orbit. You just heard a lot about what science does and looking at the Earth-Sun connection, solar system, and the universe beyond. There's a big horizon in that area. Space Technology is the directorate that really works on the technology that's enabler for space. It's cross-cutting technology like propulsion, communications, that really would map into other directorates. And then there's Aeronautics, which is really sort of the foundation for NASA, where we work on safer, secure, efficient, friendly air transportation systems. And I'm going to show you a little bit about each of these. And I'm going to start with Aeronautics, since they came first. So I'm going to run a movie here, and hopefully I can get the technology to work. There we go. this is an arena that's going to grow many times predicted over the next decade or so. So it's we're on the forefront of a very big breakthrough in aeronautics. These are real flights, not just an animation. Do we have any private pilots in the room? No. We have one. Good for you. Well, flying is a way to really sort of live aerospace every day. And, sometimes I know in a university setting it's an expensive sport. But there's also glider flying. It's a really sort of like sailing versus motorboating kind of thing. So I encourage you to, you shouldn't have your professors hear this, but I encourage you to go out and try your hand at it. It's a way to sort of experience aerospace from the ground up, let's say. So then science, you've heard a lot of this from Dr. Stofan, but I stole one of her slides because this is just fascinating to me. Each quadrant is one of the 4 divisions that NASA works on in the Science Mission Directorate. Usually takes me a while, but I think this is Earth science. Oh, and before I get into that, let me point out that the ones whose names are in yellow are in the formulation phase. Basically, they're designing, early stages of design of the mission. So these are really sort of on the books, if you want to call it that. Implementation is in orange, and that's where they're building them. Green means they're flying and they're operating. And blue means they're in extended operations, meaning they are still operating beyond their expected lifetime, and they're still giving great data, so we're still working on them. And these aren't just NASA's missions. There are ESA missions up here. XMM, I think we've got Rosetta right here, and we collaborate on many of these missions. So this is Earth science, this is astrophysics, so here's the James Webb Space Telescope, and when you look at these, I think about the technology that enables these missions. So I know we have a lot of collaborations on James Webb. I've had some involvement in that mission, and as you can imagine, there are a lot of deployments. This is a deployment nightmare in some senses, in the sense that there's this huge sun shield the size of a football field that's multi-layered and has to be deployed. The actual 18 segments of the primary mirror have to be unfolded on orbit, and then they're actually deformable so that you can phase up that primary mirror. These are the planetary missions with the inset just for those alone that are on Mars or are on their way to Mars. And when I first looked at this, I was looking for Voyager because I thought Voyager was a planetary mission, and I think it was at one point. But it seems to have gone a long way, all the way over to heliophysics now, that it's out sort of measuring the heliopause or beyond the heliopause or the edge of our neighborhood. So that might be one of the few missions that's actually migrated across this chart. But when you look at all these exotic missions, each one is a little different because the goals that it set for itself are stretching our knowledge and therefore are stretching the technology that has to make that possible. So talk about the Human Exploration and Operations Directorate. As Dr. Stofan mentioned, there's really sort of 3 phases that we're working on here. First is the Earth Reliant. That's the phase where we're doing research and preparation for the human journey to Mars. We're doing that on the International Space Station. We are also developing with commercial industry, commercial cargo and commercial crew, basically the services from the surface of the Earth up to low Earth orbit to help them bring what to the table what they do best so that we can focus NASA resources on the next steps, which are the proving ground, where we take the technology that we develop it and we go out and we exercise it. We make sure those tools work, they're effective, and they work for the required amount of time, such as the life support systems and environmental control, robotics, things like that. Because when they break out here, we really don't have the resources to instantly fix them. So we have to figure that out here in the proving ground, and then the journey goes to the moons of Mars and onto the surface. But here, the key point is you got to be Earth independent. Not only do you get infrequent resupply, even just making a phone call for help is going to take many tens of minutes at a time to get an answer. So this starts in the Earth-reliant phase, and we're doing a lot on the International Space Station right now, so let me show you a little bit about that.
10 more years presented by science at NASA. A lot can happen in 10 years. Over the past decade, an international laboratory widely known but often underappreciated has been producing results at an extraordinary rate. Using its unique capabilities, engineers have developed a precision robotic arm that helps surgeons remove tumors from the human brain. Experimenters have learned to start fires without flames, an anti-intuitive technology that could lead to super-efficient auto engines. Physicists have counted hundreds of thousands of antimatter particles among normal cosmic rays, a telltale sign of mysterious dark matter. Researchers have gathered atoms into exotic forms, creating the building blocks of futuristic smart materials, and much more. That lab is the International Space Station. The accomplishments of the past 10 years are remarkable, especially considering that the space station was still under construction, notes Julie Robinson, program scientist for the space station. Now that the station is finished, we've been granted at least 10 more. In January, the Obama administration announced an extension of the International Space Station until at least 2024. The extra time allows NASA and other space agencies around the world to pursue a number of important goals. For one thing, the space station is crucial for long-duration travel through deep space. That may sound ironic, given that the space station never leaves Earth orbit, says Robinson, but we have determined that research on station is necessary to mitigate 21 of 32 known human health risks associated with long-duration space missions. The road to Mars leads through the space station. She adds that medical research for astronauts helps people on Earth, too. Treatments for bone loss and muscle decay and advances in telemedicine are just a few of the spin-offs that have made their way into hospital rooms since the International Space Station program began. As the next 10 years unfold, a menagerie of model organisms will join the astronauts on the space station for advanced life science studies. New crew members include weeds, fruit flies, and rodents, all of which share surprising amounts of DNA with humans. By studying these organisms in microgravity, we will learn a lot about ourselves, she says. Although Robinson has a degree in biology, some of her favorite experiments are in the area of fundamental physics. For instance, she says, the station's alpha magnetic spectrometer program, led by Nobel laureate Samuel Ting, is poised for breakthroughs on the nature of dark matter. Another exciting project is the Cold Atom Lab, slated for flight in 2016. We are going to create the coldest spot in the known universe inside the space station, she says. This will allow researchers to study exotic forms of quantum matter, such as Bose-Einstein condensates. With the big blue marble looming large in its window, the space station is a powerful platform for Earth science. Sensors under construction and slated for launch in the next few years include instruments for hurricane forecasting, studies of the global climate, and lightning hazards. The extension of the space station allows Earth science instruments to collect longer-term data sets, notes Robinson. Some of our existing sensors will collect 90% more data during the extra decade.
I love that view.
The station's 10-year extension also boosts the development of America's homegrown commercial space program. SpaceX and Orbital Sciences Corporation, which have contracts to supply cargo to the station, can now look forward to competing for future contracts. SpaceX, Boeing, and Sierra Nevada are also interested in launching crews to the station by 2017. As commercial providers provide access to Earth orbit at lower cost, we move toward the day when scientists will travel to space to do their own experiments firsthand. A lot can happen in 10 years. For more information about science in orbit, visit www.nasa.gov/ISS-science. For science in Earth orbit and beyond, check science.nasa.gov.
So one of my jobs is to try to boost the technology work we're doing on station. I think it's a wonderful platform for testing out technology, robotics technology, for example. Life support systems, we're already working on that. But I'm looking for ways in which we can actually grow that research base up on station. The other thing that I mentioned that Human Exploration Operations Mission Director is working on is our next big rocket, and that's the Space Launch System, or SLS. On the left side, you see a cargo variant, and just next to that is the crew variant. It's going to go through technology upgrades over its life, starting with a 77 metric ton launch capability and growing up to about 130 metric tons is the plan. When I first came to NASA, I'd seen these kind of drawings, but I didn't realize we're actually building it at this time. So it was nice to see. This is the Orion crew capsule. It takes its first flight 3 weeks from now. Ellen and I were on a tour down near New Orleans, and we saw them building the first stage, which is basically this component right in here. These are the barrel sections that hold the tanks for the liquid hydrogen, liquid oxygen. That would feed the engines. These are the shuttle main engines. They're being brought out and prepared for flight and test fired again. And this is a case where technology plays a role not in performance. These engines are pretty good. It's really technology plays a role in affordability, basically finding a way through advanced manufacturing to be able to produce these engines more quickly and at lower cost. So the fourth mission directorate I mentioned is the Technology Mission Directorate with the big rocket and all the things we learn at station. We then have to prepare for actually going there, landing, living, and then leaving and returning home. So there's a number of things we have to work on in this environment, and that requires technology. So these are actually the areas that we've broken that out into, but instead of sort of reading through these words, I have another movie for you. And we'll show you what we're doing here.
By the mid-2030s, I believe we can send humans to orbit Mars and return them safely to Earth. And a landing on Mars will follow.
So we've been going to Mars since the early 60s with the Mariner flybys. We've been landing on Mars since the mid-1970s with the two Viking missions. We've been orbiting Mars. We've been roving on Mars since the 1990s. So in essence, humans have been exploring Mars, but from a remote site. So through our robotic explorers, we're able to explore Mars. And you probably remember the Curiosity landing that happened a little over 2 years ago. But when we send humans, there's a whole bunch of different challenges. So how do we solve those challenges so that we can be productive explorers once we get there? So that requires working on navigation and life support systems, landing systems, and so forth. Actually, these 8 areas that you saw in that previous chart. So the first thing we'll show you here is we have to work on communication. So we're working on laser communication. Think sort of HD TV coming back from Mars. We're also working on navigation using pulsars, an interesting natural effect that you can use for navigation. Lightweight structures help us build lightweight rockets so that we can put more payload to Mars. Also ways to do efficient solar electric propulsion to move cargo. Bigger and better landing systems, some propulsive, some inflatable, would help us to land larger cargo onto Mars. Supersonic parachutes, robotics to help us explore, particularly in hazardous environments where we may not want to put the human in that environment, so that we can use robotics working with humans to help with the exploration. Ellen had mentioned the radiation, not only from the sun, but also the galactic cosmic radiation, how to protect from that. We have to recycle. We have to recycle our air, our water, and on station we're getting that up to a pretty high efficiency, but it's not 100%. We have to generate power. We have to store power on the surface. So there's a number of ways to do that we're exploring, developing techniques to do that. We also need to do in situ resource utilization. So for that part we can't recycle. We have to be able to either ship that, which is expensive, or we extract that from the environment. So those are the kind of areas that are the technology challenges that we're working on in preparation for this mission. So let me show you one here, which was conducted, let's see, it was in June of this year, and it's for an advanced entry system called Low Density Supersonic Decelerator.
On June 28th, NASA's Low Density Supersonic Decelerator project conducted the first shakeout flight of a new way of testing technologies that will one day be used to land heavier, more massive payloads.
So they had to launch this to high altitude to replicate the environment that you'd see in the Martian atmosphere.
Scientific balloon to hoist a 7,000-pound test vehicle to an altitude of 120,000 feet. The test vehicle was then released from the balloon, spun up for stability.
It's hard to stand this close to the screen with the spinning, but
4 times the speed of sound and an altitude of 180,000 feet, a condition very similar to the conditions it would see at Mars. Once we reached the correct speed and altitude, we despun the vehicle. And then we got a chance to test our new supersonic inflatable decelerator. The camera lens covers deployed. We see that inflated very uniformly without disturbing.
so by increasing the size of the
previously unreleased
entry shield there, you know, you get the drag,
speed video
you get the drag
taken
up.
during the test. We used the supersonic inflatable decelerator to slow us with something closer to 2.5 times the speed of sound. We use a balloon to help deploy the new supersonic parachute. The balloon is shot out the back of the vehicle at over 200 feet per second, and then we cut the balloon free and it begins to pull the parachute off the back of the vehicle.
Something went wrong.
As the parachute begins to inflate, we see one of the surprising aspects.
But this is why you do tests.
Which is the early onset of tears in the parachute. We see where those tears began.
So I think it's going Mach 2.5 here.
And otherwise how the parachute behaves.
And it had a bad
and
day.
Trying to inflate behind this very blunt object moving 2.5 times the speed of sound, punching a hole in the atmosphere and creating an extremely turbulent, chaotic environment for the parachute to exist in. We now have a data.
So the key is from you'd rather find this out here than find that out on the way onto the Martian surface. And so the key is it's okay to fail. That's where you learn about what works and what you need to learn more about. Because if all the tests you do work, then you know that in that environment it works. You're not being aggressive enough. You don't know yet what you still need to learn. So the real trick here is to make sure that when things fail, you actually learn from those tests. So the only failure is the failure to learn. So here they instrumented the system properly. They actually got the team back together and they've had a lot of great insights on how to improve on this design. So let me leave you with two sort of final thoughts here. I'm always interested in figuring out how to get involved. And so here are two thoughts. This one is about space station. I was very pleasantly surprised how NASA works its payloads. They have a thing called the National Lab structure, where as an experiment developer, you launch your hardware up to station, you test it, and in return for the free launch and for the crew time and all the resources on station, when you're done with it, they adopt that hardware into the National Lab. It's sort of like their storage locker. So it becomes inventory that others can use because it's expensive and it takes a lot of time to get experiments up to station. So now, as a researcher, perhaps with modest resources, if there's something already on station that you could use to do your research, either without putting up new hardware, but perhaps by putting up new software or by changing how it's operated, then pretty quickly you could get access to that equipment and you could do your research. So I know there's one facility, it's very close to my heart, but it's one facility that's up on station where we've done this with ESA member nations. It's called Spheres. It's these little satellites that fly around inside Space Station. And we've been running for 4 years in collaboration with ESA, a high school competition called Zero Robotics. I don't know if anyone's heard about that. I know that a few high schools in Europe actually in the UK have been involved in the program, but that is a research facility that that is very likely accessible to you if you are interested in doing controls and associated with multi-satellite close proximity kind of operations. But there are also other facilities, there are many facilities up there. If you go to this website, you could take a look there, see if there's something that's related to the kind of work you're interested in doing, and see if there's something you might be able to use. Another area is just to reiterate on what Ellen said. If you go to nasa.gov/solve, there are a number of, as evidenced by the Ann Moore down here, there's a number of different challenges out there. Some are cash prizes, some are open internationally, and there are a lot of interesting areas. Some are technical, some are science-based, and so forth. So I encourage you to go to that site as well. So I'll just close with saying that Mars is really the ultimate destination for as far as we can see for humanity, because having looked at all the other planets and destinations in the solar system, it's obviously the most friendly to us and has the most resources that are readily available. But it's a very difficult mission. And that's why it's not a mission just of one mission directorate in NASA. It's not just NASA's mission. It's really an international mission that we're only going to be able to accomplish with partnerships between commercial, science, human, technology, and international partners. So I encourage you to join us on our journey. And I'll encourage Ellen to come up here. The deal is I get the easy questions, and Ellen gets the hard questions, and we'll take it from there.
I think we should thank our speakers again. Well, I think you'll probably all join me in saying how inspirational those two talks both were, from the point of view of being very privileged to get such an up-to-date insight from the people at NASA who are making these things happen, and also this call for collaboration as well, which I think is really inspirational. And having you here this afternoon is especially special because UCL has worked with NASA right from the beginning. So in the 1960s, I think we had the first missions together called the aerial missions. And also UCL was the first university in the UK to do space research. So we are really very happy that you've been able to come over this afternoon. Now, we have our two speakers for about another 20 minutes, so the floor is open to questions. There are microphones towards the back, or otherwise speak up and I will relay the questions so people on the webcast can hear. I can see a lady with her hand up. Yeah.
I'd like to know if each of you might be able to comment very briefly on whether there is a particular attribute you have, or an experience that you had, or an opportunity that you were given throughout the course of your education that brought you to where you are today that you think would be helpful for people here to know about.
That's an easy one. I'll go first. So it really wasn't my choice. It was actually my mother's choice. She had studied mechanical engineering during World War II, and when she was very interested in rocketry and read everything about human exploration, which into space, which hadn't happened yet. So when I was a little kid, probably about 4, she would she would always sit me down in front of the TV to watch the Gemini and I don't even remember the Mercury flights, but the Gemini flights, and then she'd keep me home from school. And I remember the phone would ring, and she'd be yelled at about how, I'm not getting an education. And she would yell right back and say, he's getting a better education. So I was kind of programmed, and it wasn't my choice, but I don't regret it.
It's funny because in a way my story is sort of similar. My father worked for NASA, so I went to my first launch when I was 4. I'm kind of a NASA brat. But I will say, to me, it was the influence of individuals. My mother was a science teacher. There was a professor, and of course she was who was a geologist, who answered all of my questions and made me think that geology was really cool. I got to go to the Viking launches, and I'd go to hear Carl Sagan speak. And so that importance of seeing the fun of science firsthand from people who actually do it, who build space missions, who operate them, I think it's that people thing that to me is inspirational. Well, I will say our administrator for science, John Grunsfeld, who's a guy who actually went up in space and repaired Hubble, his favorite thing to say is our NASA missions accomplish no science. The Curiosity rover has accomplished no science. It's the scientists here on the ground who built Curiosity. It's the scientists here at UCL and all over the world who are interpreting the data. Those are the real explorers.
I'm glad you finished that sentence. There's a question up the back there.
Hi, thank you. Thanks for coming to talk to us today. I just wanted to ask, kind of, what is the most promising or convincing physiological evidence that you've seen, kind of from the research that's been done on the ISS, that makes you think that we can actually get cosmonauts onto Mars?
I think what I've seen, and this is something that is kind of shocking to all of us on some level, but what we've been finding with the ISS is the better exercise protocols we can give the astronauts, lower salt, fruits and vegetables, not too much fat. Does this sound familiar to anyone? The more we can mitigate a lot of those health effects. You know, you live a healthy life and you end up healthy. It works in space, it works on the ground. It's hard medicine for all of us to accept. And so I do think that we'll be able to mitigate most of those health effects. Some, like the radiation, it's going to be a balance between mitigating it and accepting a higher risk. And that's a global conversation to how much risk are you willing to take on. But I think we can mitigate them down to an acceptable level, and I think our research has been showing that.
I would agree with everything except for broccoli, as long as we can avoid that. I've been very pleasantly surprised with the life support systems. The life support system that used to be on station has been upgraded multiple times. I mean, we're getting to the point of 90% recycling, which you can think through that, recycling of water and so forth. You can think through that, and I won't go into it, but you know, we're getting there, and we really have to. I mean, you got to be that efficient in order to. Otherwise, you got to take too much luggage along, and we just can't do that. So.
There's a microphone is now over here.
I've read that funding has steadily been decreasing for NASA. I was just wondering what your thoughts were on why that's happening and what the implications are.
See, he's only been in this job 6 months. I've been here a year, so I get the budget questions. No, I'm used to answering. You know, our budget actually for the last several years has been quite healthy. Obviously, the U.S. federal budget, like budgets all across the world with the global recession that went on in 2008, you know, science budgets all over the world have suffered. There's no two ways around it. But for the last several years, we've actually seen a lot of bipartisan support for NASA. Now, our budget is certainly well below the levels it was at Apollo. So when you look at an undertaking like we want to go to Mars, you can say, is there a disconnect? And I don't think there's a disconnect, because I think the way we're going to get to Mars is, first of all, it's not just the U.S. We're going to partner with the globe, which helps diffuse the cost across all of us. And I also think private industry has a new and interesting role to play. You know, David talked about commercial cargo. We have commercial crew that'll start launching, SpaceX and Boeing will start launching astronauts from U.S. soil in 2017 timeframe. So I think the whole commercial sector has a really interesting role to play that this administration in the U.S. has been really supportive of. So it's a different model that we're going to use going forward.
And maybe you could say something about things like the Google Lunar X Prize as well, in that sort of drive to commercialize space.
Well, where I was going to add on was, you know, the administrator, and I agree, says that, you know, funding is about choices. And reduced funding, where really it's been sort of flat funding, but due to inflation, its buying power goes down, means it's about tough choices. And so I think things like really engaging the commercial sector is probably enabled by that environment. And I think that's an essential role that the broader community come in here. You know, we've seen in the commercial sector, as they've been able to launch cargo to station, they're starting to attract other business. So that has a payoff, you know, for launching satellites and so forth. That's a payoff that's very powerful. So sometimes you can do, you know, when you have a restricted budget, you can do something radically different. And I think if you do the right things, then that can actually be better. So, did I avoid your question?
Well, no, that's fine. I was just thinking that it was a really good point, because the whole global view on space science is changing and evolving, and therefore the role of NASA is evolving. So everything you were talking about, humans going to Mars, that's where the place for NASA is now, and other people can come in and do things that NASA pioneered in the decades before. Challenges
have been very instrumental in aerospace for a long time. Early stage of aviation, you know, there were a lot of these prizes. The human-powered Kramer Prize, human-powered aircraft, really led to lightweight and composite structures and things like that. The Kramer Prize there was instrumental. So the X Prize is is another one that I think is great. And, you know, good ideas come from everywhere, and you can't shut that out. You cannot become an insular kind of agency thinking that all the good ideas are with you. They come from everywhere. So these prizes and challenges, I think, are key to engaging that broader community, and that's essential.
Yeah, I was just going to add, it's been interesting for the agency to let go of things, because you have to say, where does our focus need to be? That's about, you know, Charlie, the administrator's choices. Our focus is going to be on going to Mars. So what can we let go of, even if it's hard to let go of because it's something you've done for a long time. But if you say the commercial sector can do this just as well, if not better than we can, we got to let it go.
Thank you. There's microphones over there with that gentleman, and then we'll come down and then over.
Okay, I've got a question about the radiation when you go into Mars. You've touched on it a couple of times, but if you look at the data from RAD instrument on MSL Curiosity, it suggests that in the time taken to get there, get back and spend time on the surface, you probably have pretty much a lifetime's exposure to radiation by the time you get back to Earth again. One obvious way of reducing that is to actually get to Mars more quickly. Instead of spending 8 months there on a minimum transfer orbit, you basically power to Mars. So when do you think we're going to be in a position to actually get to Mars more rapidly than currently?
Oh, thanks. Well, I think one of the things you want to think about, it's really a multifaceted solution. That's one of the facets. The other is the shielding. The other one is, you know, there are a lot of dangers in spaceflight, and you've got to balance the radiation danger with other dangers associated with launch and landing and so forth. And so I think getting there faster, you're either talking about hybrid chemical, solar, electric, which is being studied, or you're also talking about nuclear thermal or nuclear electric thermal. But I think nuclear thermal is probably the more promising right now. So we are funding work in all those areas, not at the same level, but clearly the less time you spend exposed, the better. There are a lot of challenges to testing nuclear thermal, and as you might imagine, and we're trying to figure how to deal with that. So.
Yeah, the other area that I think is really interesting is this whole issue of, you know, humans' reaction to radiation and our ability to repair damage, and it varies from individual. There's a lot of really interesting research going on. This is obviously an issue for people here on Earth also who get radiation therapy for cancer. You know, you can get collateral damage, so to speak, from being, you know, trying to kill a cancer, but then it destroys other cells. So people are very interested in ways, how do you mitigate radiation effects on people, not just for astronauts, but here on Earth. And I think there's a lot of really interesting but very early stage research going on in that area, and also on the fact that different individuals react more than others. And so can we, in the future, how will we select astronauts? How will we do it based potentially on their ability to have better radiation repair than another individual? I think there's all kinds of really interesting avenues down that road.
Okay, thank you. There's a question at the front.
Okay. So in the 60s, I think it was, there were futurologists that predicted that middle-class families would be having holidays on the moon, and Pan Am had a list of names of people who wanted to go into space. I just wondered when you think that will happen, if ever, and would it be possible to go to Mars as well and have holidays on Mars?
Well, we do have lists of people that want to go into space. You could see, you know, there have been a number of well, they don't want to be called tourists. But private astronauts, privately funded astronauts that have gone, and I think there's a long list that are all lined up to do that, and we're waiting to see that industry take off. You know, in any of these industries, whether it's the airlines or space, you know, the more you fly, the cheaper it gets. So, because you just amortize that cost across all those passengers. So commercial so space tourism could be a breakthrough for human spaceflight and getting the cost down. I remember when 2001 Space Odyssey first came out, going to that movie, and I said I wanted to go to Jupiter, and thought, oh, it'll probably take maybe 40 years. Hasn't quite happened yet. So Ellen's good at predicting things. So.
Well, I think the positive thing, because people have been talking about this for so long, and I think many of us who are interested in this and who love science fiction and increasingly want to see things in it actually happening, I think we can be encouraged because we have companies like Virgin Galactic, we have companies like SpaceX and Boeing that are going to be starting to launch commercially humans. So that's the first step, and we're there. And so the second step of having it be routine commercial space tourism, you have to get through the first step, and that's the stage we're in right now. And it's a tough step, and it's going to take a while, but I think we're going to see it happen.
Okay, we'll move on quickly to the question at the back.
Hi, Ellen, when you talk about climate change, you were very careful to say you were presenting the data, but not having an opinion or trying to judge. Does NASA have a policy or particularly to engage with the American people about climate change, or do you think scientists have a responsibility to not only present data but also to engage with society at large?
NASA certainly has a position on climate change. We're completely in line with the policies of the IPCC that climate change is caused by human effects, and the effects are becoming more noticeable, as I was showing in the Arctic and Antarctic, and it's happening every day. Our role at NASA is to collect the data to try to help the models go better in the future. It's to try to explain the data as clearly as we can to the public, and we try to do that with our websites. We try to do it. I talk about it now every talk I give because I show that video, and I can't tell you how many people have come up to me after a talk where I've showed that video and said, I never realized this was happening. And that's so frustrating to me as a scientist that we have had such a hard time communicating the facts of climate change to the public. Excellent report that came out this year that Chris Rapley here at UCL put together on communicating climate change. If you haven't seen it, it's a great report. Huge frustration from the scientific community of how we communicate to the general public. At NASA, I feel very strongly that our role is to be out there talking about it, putting the data in front of people so they understand that it's not a model, it's happening right now. The effects are getting more and more noticeable every day. We have towns in Florida right now that at high tide are having to pump out streets. You know, what more evidence do you need than that? And you know, the scientific community has it on us to try to make sure that these data are clearly explained to the public, and certainly NASA plays a critical role in that. And the administration has been unequivocal on their support of trying to get this information out and doing what they can to try to mitigate what's happening.
Yeah, and I think from our point of view, we always look to NASA as a leader for public engagement with science. So I think you put your money where your mouth is on that. We've only got time for two more questions, which are lined up. One over here, and then the gentleman on the side there.
Yeah, thank you. I was just wondering about the effect of finding evidence of life beyond planet Earth on humanity, on our civilization and probably, you know, religious beliefs. Do you think we're ready for this?
I really think we're ready. I think humans are capable of taking on new information and moving forward. You know, to me, it's so exciting. You know, is it going to have RNA and DNA? Is it going to be virtually unrecognizable? Is it going to be completely what we expected? You know, the parameters on what we're going to find and then the implications of that, I think are just tremendously exciting. And I think the public is ready for it. I think the world is ready for it. And I think it is going to have a profound effect. I mean, when you think of that question of are we alone, and people looking up into the night sky for thousands of years and wondering about that, and the fact that it's within our grasp to actually answer that. We know the destinations in our solar system, where to go. We know what to measure. It is within our grasp, and we will determine this in our own solar system in our lifetimes, and I think it's tremendously exciting. And when I say we, I mean we, the international we, not the NASA we.
And I've been involved some in working on technology for the exoplanet search, and I find that community fascinating. It's everywhere we look to the resolution and sensitivity that we can see, we're finding more and more planets. So as technology helps make better sensitivity, better resolution, they're going to be there, and we're getting really close to the size that we're used to here. And you know, so you can almost predict, it's like a Moore's law kind of effect with computational power. You know, you could almost predict the date in which we're going to, you know, really see Earths. And then when you see them, you get their spectra, and you see, do they have water, do they have oxygen, do they have methane, non-equilibrium gases, which must be renewed, otherwise they sort of burn or whatever. So they must be renewed by some active source. Could that be life? That's real soon, right? Promise?
Yeah.
Good.
You heard it here. Last question.
Thank you for a nice talk. Could you tell me about the rehearsal flight to Mars? I guess you will have some rehearsal flight to Mars because you have Apollo 8 and Apollo 10 before Apollo 11. So flight to Mars is not a single flight. It should be a sequential flight. So could you tell me about that?
You know, it's something we're working on right now, because clearly we've been spending a lot of time talking about that, because we're not going to get to Mars in one go. We're not going to, right now we're working on something called the Asteroid Retrieval Mission that some of you may have heard of, where we're going, we take a boulder off an asteroid, bring it back to near the moon, send astronauts out there to practice all those skills, test the solar electric propulsion, you know, using the Orion, using the SLS. So, okay, that's our first step. So what's next? Certainly in the meantime, we're working at Mars with our robotic spacecraft, doing some of those things I talked about to get ready. But clearly then at the next point, there has to be, what is it we demonstrate next? Is it a round trip with no humans? Is it really serious in situ resource utilization on the surface of Mars, again, an unmanned mission? So what are the manned and uncrewed missions that we need to do between now and the 2030s to make sure we're ready? And we're working on it. We're having lots of meetings on it, lots of view graphs, but we're not there yet. And because, of course, it also has to be affordable.
So currently, the first flight of SLS is supposed to be in 2018. Now, that will be uncrewed. And then the second flight of SLS, I think, is around 2020. Don't quote me on that. But that will have crew, and I think that's to go out to cislunar locations. I think one way that helps me think about it is if you've studied the history of human space flight back to the Apollo era, the Gemini flights the Mercury flights, which went first, were sort of, can we get to orbit? Can we live? Can we get back? And I sort of think that's analogous to what we're doing with commercial crew and some of what we're doing with space station. Then there were the Gemini flights where we would actually exercise the technology, see if we can work for long durations in space. And that's what we want to do at cislunar environment. But then there were a series of science precursors to the moon. There were Surveyor and Ranger spacecraft. That's sort of what we're doing now in partnership with the science missions, finding out about radiation, finding out about the weather. And then comes the Apollo era where you go. So I find it useful to think in those kind of parallels.
Well, thank you very much for those questions and those answers. I am afraid that we are out of time, but I hope you found that as inspirational as I did. I love the message that this is an endeavour by humans for all of humanity, and a very nice message that it's for all of us to get involved. Don't forget that the European Space Agency is landing a probe on a comet for the first time in about, I think, half an hour's time. So please do go away and look at that. But let's thank our speakers again.